Hello and welcome to lecture 9 of the course Theory of Computation. Right. In the previous lecture, we saw NFAs and that NFAs are equivalent to DFAs as far as computability is concerned. Meaning, whenever there is a NFA that recognizes a certain language, there is also a DFA that recognizes a certain language. So, it is almost immediately clear that NFAs are at least as powerful as DFAs. Now, with the observation that every NFA has an equivalent DFA, right, it implies that the class of languages recognized by NFAs are the same as the class of languages recognized by DFAs, and this is what we already know as the class of regular languages. So, this gives us another definition or another characterization for the class of regular languages as so if a language is regular, or a language is regular if and only if there is some NFA that recognizes it. Okay. So, now if you recall, we showed that regular languages are closed under complement. We showed that regular languages are closed under the union operation. So, now we will use this to show closure under other operations as well, namely the regular operations, right. So, the regular operations were 3: union, concatenation and star. We already saw closure under union using a Cartesian product DFA. Now, we will see a simpler proof which uses NFAs, and followed by quite straightforward proofs for the closure under concatenation and the closure under star operation. Okay. So, let us first see the proof that regular languages are closed under union that uses NFAs, right. So, we already saw the proof using DFAs. So, let us see. So, to begin with, we say that so we have to show that, let us say, if A1 and A2 are two regular languages, their union is also regular. So, let A1 and A2 be two regular languages. So, we may assume that there are NFAs recognizing it, right. So, we may assume that N1 and N2 respectively are NFAs that recognize A1 and A2. So, now the goal is to build an NFA that recognizes the union. Okay. So, let us say N1 and N2, the ones I have just drawn them, N1 at the top and N2 at the bottom. So, now in the left we have the N1 and N2. So I am not going to do a full proof in terms of the extent of details. It will be more, the proof will be more depicted pictorially. One reason being, we have already seen one proof, but even the pictorial representation will be fairly clear, is what I feel. So, suppose N1 and N2 are the this is N1 and this is N2. These are the NFAs that recognize A1 and A2. So, notice that there is one starting state for N1, one starting state for N2. N1 has one accepting state, N2 has 3 accepting states, and then I have depicted some extra states, right. Of course, I have not represented, so there could be many more states. I am not bothered about them. There could be all the transitions, there will be all the transitions, which I am not writing down. Just think of them. The only things that we will require are the start state and the accepting states, right. So, that is the extent to which we will operate on this, right. So, what we will do is, so we will build an NFA that which actually combines these two NFAs, such that the combined NFA, right, the combined NFA will accept a string if and only if either one of the NFAs accepts a string, right. So, what we want to do is, we want a structure by which either NFA N1 accepts or NFA N2 accepts. If either one of them accepts, the combined NFA should accept. The simplest way is to do the following. We want some kind of a redirect, right? So you want the capability to choose, do you want to try N1 acceptance in N1 or N2, right? So you want to try acceptance in either in one of them. So the simplest way is to add a new start state. Okay, you add a new start state. Just 1 second. So maybe I'll erase this labeling of N2 here. Maybe I'll write it below. Right, I'll add a new start state, and then what I will do is I will add transitions. I'll add transitions to the existing start states of N1, okay, and existing start state of N2. So this is a new start state. Let me call this start state, let's say I'll call this Q0, okay, and from Q0 I am adding transitions to the start state of N1 and to the start state of N2. But on what symbol should this transitions be? It should be empty string, right? So these are both epsilon transitions. So this NFA is like this. So initially there is Q0, which is a start state, and from which you could make epsilon transitions to either the NFA N1 or the NFA N2. The transitions inside N1 and N2, whatever they were, they will remain intact. And once you make the epsilon transition, you are now, let's say you move to N1 using the epsilon transition, okay? You move to N1, and now you will just get stuck or you will just operate inside N1, after which there is no going to N2, and then you get accepted if after reading the string you are at the accepting state of N2, right? So which is the way, the only way to get acceptance inside N1 is if you entered the accepting state. So that is when the string is a member of A1, and similarly the only way to get accepted through an accepting state of N2 is if the string is a member of A2. So the start state is the new state Q0. The accepting states of the new NFA will be all these accepting states. So the accepting state of N1 and the accepting states of N2, all of them. So they have multiple accepting states, all of the multiple accepting states. So now here there is one accept state of N1 and 3 of N2. So now in the joint machine there are 4 accept states overall. Whatever was inside N1 and N2 remain as it is, right? So just to note, if N1 was, let's say, Q1 sigma delta 1 small q1 f1, and N2 is Q2 sigma delta 2 small q2 and f2. The new one, let's say the new machine, let's call it N, okay, let's call this machine N. Let's say if N is Q sigma delta Q0 and F, then we can actually write down all of this, what is Q, what is sigma, what is delta, etc. Okay, sigma is the same for everything, but let's say Q, for instance, is, you have Q1, the states of N1, together with the states of N2, Q2, together with the new state which is Q0, right? And F is the union of the accept states of N1 and N2. So it's F is the F1 union F2, right? So nothing new is added. And similarly, you can so Q0 is new, the start state is new. So I've almost said everything. The only thing that is a bit more involved is the the transition functions. That requires a bit of detail. You may have a look at the book on how they explain this. Okay, so just have a look at the book. The details are provided there. Sorry. Okay, so yeah, so please go through this and try to understand. Okay, so the next result, the next closure property is the closure under the concatenation operation, right? So we just saw the union operation. In fact, we had already seen a proof. This is a new proof using NFAs. So let's see the proof for closure under concatenation. So similar to what we just saw, let A1 and A2 be the two regular languages, right? And so because they are regular and because we have the new characterization using NFAs, we can assume that N1 and N2 are the two NFAs or are two NFAs that recognize A1 and A2 respectively. Okay. So now let's say N1 is the one on the left side, right? So this is N1 and this N2 is the one on the right side. So both of them have one start state, right? So obviously there is a unique start state for each NFA. N1 has 2 accept states and N2 has 3 accept states, right? And now we want to combine these N1 and N2 in such a way that we want to somehow build an NFA using N1 and N2 together, so that the combined NFA accepts the concatenation language, right? So what we will make use of, so I've again drawn them, so maybe I'll just move it a bit more below. So this will be our working copy. Okay, so now we want to somehow add things to this N1 N2, so that and we want to make it into one machine, right? And such that this one machine accepts the concatenation operation, right? So what is concatenation? Concatenation language means W will be in the concatenation language if the string W can be written as, right? If the string W can be written as W1, W2 as a concatenation of two strings, where the first string is in A1 and the second string is in A2, right? So what we are trying to do here is we first pass the string through N1 and then we want to pass through N2, right? If you recall, right after we proved closure under union using DFAs, we discussed this possibility. The issue was that if you have just one string, the string is itself a string consisting of symbols, right? But we don't know where to split into W1 and W2. That was the issue with the proof using DFAs. But in the case of NFAs, this can be handled because NFAs have the capability of non-determinism. So the NFAs itself, we can have the capability inbuilt or inbuilt in the construction, such that there is an accepting computation if there is some way to split this string W into W1 and W2, such that W1 is in A1 and W2 is in A2, right? So that's our goal. So we want to accept W if there is any way of splitting. Like it could be the first symbol of W and last n-1 symbols of W, or it could be the first n-1 symbols of W in A1 and the last lone symbol accepted by A2, right? So it could be any of these possibilities, but whatever be the possibilities, W will be accepted if there is such a possibility, right? So this non-determinism comes in handy here, right? So that's why it didn't work in the case of DFAs, and that's why it will work in the case of NFAs. So let us try to see what we need to do. So we first have N1 in the left side, right, which is the NFA for A1, and N2 in the right side. So like before, we are not going to bother about internal states of N1 and internal states of N2 and all the internal transitions. There is no change for any of that. The only operation that we will do will involve messing with the start states and the accept states of both N1 and N2. Okay, so what we will do is, we at any point, like if we want to see if the string can be split into W1, W2, where W1 is in a string in A1, which means W1 ends in an accepting state of N1, and then W2 starts, meaning there should be a way to go from the accept states of N1 to the start state of N2. So what we will do is, we will have epsilon transitions from the accept states of N1 to the start state of N2. And now the rest so now the only strings, if you see, the only strings that will get accepted in this combined machine are, so now notice that, okay, in my figure the accept states of N1 are still listed, are still drawn as accept states, so that should not be the case. So now let me see if right, so I'll just draw them as, these are not accept states, right? So this, maybe I'll just put some, this were accepting states of N1, but now they are not, right? So I'm just indicating that by this dotted line. So don't think of them as accept states. So these two are not accepting states of the combined machine. Okay. So this is our combined machine, and let's call it N. And the accept states of N would be just the accept states of N2. So these three will be the accept states of N. So the only way to, if you see what is happening, if there is any way to split the string into W1, W2, such that W1 accepted by N1 and W2 accepted by N2, that way we can accept, after, when you are done processing W1, you will be at an accepting state of N1, and then you can take the epsilon transition to the start state of N2, which is no longer the start state of N, right? And then you can complete processing W2, which will take you to an accepting state of N2. So that's it. So just couple of details. Start state of N is the start state of N1, and accept states of N will be the accept states of N2. So, and the rest of the detail you can see in the book, but pretty much this is the proof. It's quite simple. We don't tamper with the internal states or the internal transitions. We just make the start state of the N1 the start states of N, accept states of N2 the accept states of N, and we just add epsilon transitions from the accept states of N1 to the start state of N2, and that's it. This is our NFA that accepts the concatenation language. So now you can see it's very simple, much more simpler than the Cartesian product idea for the union that we had using DFA. So this must give you some idea of why NFAs are useful, right? How we are harnessing the power of non-determinism to be able to prove quite easily what we want, right? So that is the next the closure under the concatenation operation. The final regular operation is a star operation, right? So now we want to show closure under the star operation. So the claim is that the class of regular languages is closed under the star operation, right? So like before, we may assume that I can say, maybe I'll just move this a bit down, right? So we want to show, let A be regular and N1 be the I think I may be saying it below. So it's already written here, so I don't want to repeat it. I'll just erase this. Also move this back up, right? So let A be regular. So A will be recognized by some NFA. Let us call it N1, right? Which is given by N1 is Q1 sigma delta 1 small q1 and F1, and our goal is to construct N, right, where N has a states Q, the alphabet is the same sigma, and delta is a transition function, Q0 is the starting, and F is the accepting function, right? Now such that we want to construct N such that the language recognized by N is a concatenation, star of A, which means it should be a concatenation of some number of strings
each of those strings should be in A. Right? So the sum number is not specified. It could be 1. It could, like it could vary also, right? So it could be 0, 1, 2, 3, any numbers, right? So when you take 0 strings from A, it gives you the empty string. When you take 1 string from A, it is just the language A itself. If you take 2 strings from A, it is like A concatenation with itself, right? So it's the union of all of this gives us the star. So now what we have is the, let's say this is N1, right? So this is the NFA for N1. Let's say this is the start state of N1. Now how do we modify this in such a way that right? How do we modify this in such a way that we accept all the star operation language? So now, so the idea is kind of similar to what we saw here. So here in concatenation, after going through N1, we want to go through N2. But here there are no two languages, there is only A, right? So now we want to accept A star, which means we want to be able to come back to the, we want to be able to, like, let's say if one string breaks into two pieces, let's say W breaks into W1, W2, where both of them are in A, W1 and W2. So basically we want to pass through the NFA twice, or it could be three pieces, W1, W2, W3. So we want to, and each of them are in A. So we want to go through the NFA thrice. So after getting to the accept stage, we again want to come back to the start state and again should be able to go. So the simple idea that we have to execute here is to add epsilon transitions from the accept states of the machine to the start states of the same machine, to the start state of the same machine, right? So that's what I'm doing here, right? So I am adding epsilon transitions from the accept states to the start state. So now this will accept, now this and the start state remains the same and the accept states also remain the same. Now this will accept all strings of the form x1, x2, etc., where each xi is in the language A, right? But there is one small issue here. The one small issue is that the star operation, so any language A star, this usually contains the empty string, right? Because in this definition, right, A star, we can, in this definition over here, we can have k equal to 0, which means there are no strings, like there is nothing, and that gives us the empty string. So for any language A star contains empty string, right? For any language A. But here, if the empty string has to be accepted, right? If the empty string has to be accepted, there is only one way. You have to have the start state as an accepting state, or maybe you should have an epsilon transition from the start state to another state which should be an accepting state, right? But we don't know whether we just took a general language A and the NFA corresponding to it N1. We don't know if these properties are satisfied in this NFA, right? So for instance, A may not have epsilon in its, A may not contain epsilon. So the start state of A may not be an accepting state, right? If the start state is an accepting state, then A contains epsilon, right? So we cannot insist that the start state will be an accepting state. And if we modify the start state to be an accepting state, that can cause other problems, because if we modify the start state, if we make the start state to be an accepting state, then whenever in between computation you reach the start state, you may end up, there is a possibility of accepting, and this will result in extraneous strings getting accepted. So we cannot just convert the start state into an accepting state. So we want another way to accept the empty string, not by modifying the start state, because that can cause, like suppose there is some okay, suppose there is some computation where you go there's something, right, and this ends up being accepted if you make the start state being accepted, being an accepting state. So we don't want to do this, right? So we have to have some other way of accepting the empty string. So what is the other simplest way? The other simplest way is to just add a new start state, which is an accepting state, right? So you add a new start state, which is an accepting state. Let's call this Q0, right? So this old one was, say, Q1, and we have an epsilon transition from Q0 to Q1. So now the start state will be the empty string will be accepted because the start state is an accepting state. So the empty string is automatically accepted, right? And now so now what is n? So the n is this. Maybe I'll just again I'll just pull it down a bit so that I can draw a box around this. Right, n is this. This is our n, and the accept states of n are Q0 and the original accepting states of n1. So which is this, and the start state of n is small q0, right, small q0, and that's it. So now we are accepting both the empty string as well as x1, x2, x3 or x1, x2, x3, x4, where each of these xi's are in A1. So let me just list down what all we did, right? So one is that we added epsilon transitions from accept states of n1 to the start state of n1, and second thing, to ensure that empty string is in the language, right? So unless q1, which is the start state of n1, right? So this is q1, right? The start state of n1 is q1. Unless q1, which is the start state of n1, unless this is an accepting state of n1, right? F1 is the set of accept states of n1. We need to, okay, maybe I'm kind of running out of space, so maybe let me see what I can do. Oh, sorry. Okay, maybe what I will do is I'll just push this back up a bit. Okay, sorry. Okay, so unless q is in F1, epsilon string is not accepted, right? So then we add a new start state q0. We add a new start state q0 and have epsilon transition from Q0 to Q1. So that is the extent of the construction, right? So you added these loops, epsilon loops from the accept state to the start state, and then you add a new start state and have an epsilon transition from the new start state to the old existing start state. And so in this, so since we didn't write down the details of the earlier one, we'll write down the details. But before that, I hope the idea is clear. That this indeed accepts all the strings that are in A star and does not accept any other string, right? So if you can see the only string that it accepts through Q0 is the empty string, right? Because you can never come back to Q0, and the only strings that it accepts through the original accepting states, whichever ones they are you do some transitions, you come to the accept state, and then you again go back to the start state and again come back to the accepting state. So it must have gone from start to accept some k number of times, right? Which is exactly the star operation, and nothing else is accepted too, right? So let me just in this particular closure proof, I want to just write down the what is Q, what is F, what is transition function, etc., right? So as already mentioned, N1 is the NFA that recognizes A, or N1 is one of the NFAs that recognizes A, and our goal is to construct N which recognizes the A star, right? And Q1, sigma, delta 1, small q1 and f1 are the phi tuple corresponding to N1, and for N the things corresponding things are Q, sigma, delta, Q0 and F. So what is Q here? Let's try to write down what is Q. Q is nothing but the only new state that is added is Q0, right? Q is nothing but Q union Q0, where Q0 is the new start state, right? And what is F? If you see, all the old start states or all the old accepting states are still accepting states. In addition, Q0 is also an accepting state. So F is also, so Q is Q1 union Q0, F is F1 union Q02, right? So in the case of F is also the newly added start state is an accepting state in addition to the existing accept states. Now let us consider the transition function. So the sigma is the same, start state is already done. The only thing that is remaining is the transition function. So now let us consider all the transitions, right? So what is delta in terms of the existing transition function? So let us first consider QA, the pair where Q is some state and A is some symbol which is not the empty string, right? So, So in the existing transitions will be the same as the existing transition delta 1 of QA when Q is in Q1, right? It's an existing state, not the newly added state, and A is not epsilon, right? Because whatever is not epsilon, the only new transitions that we added are the epsilon transitions. And what if what about Q comma epsilon for the existing states Q, right? So if you are an accepting state, right, you are adding these new epsilon transitions. If you are not an accepting states, you don't have to do anything, right? So this is also delta 1 Q comma A when Q is not in F1 and A is not epsilon, right? This is also the same. But when Q is in F1, when Q is in accepting state, right? Okay. When Q is in F1, right, what is it? So when Q is in F1, what is Q comma epsilon? So it is possible that from this accept state, there was already some epsilon transitions to some other states, right? So some other epsilon transitions may have existed. So now we are adding a new epsilon transition. So what we have to say is, whatever was already there, delta 1 of q epsilon union q1, where q1 is the start state, old start state, right? And so this completes all the transitions of the existing states. So we first wrote all the transitions of all the states except epsilon transitions, then epsilon transitions of all the states except the accept states, and then the epsilon transitions of the accept state. That's the three ways we split the thing. Right? The first one is all states but not epsilon transitions. Second is non-accepting state of the original machine but not epsilon transitions. Then accept states and epsilon sorry I didn't need this. This is an error. Right. First is all states but not epsilon transitions, then epsilon transitions of non-accepting states, and then epsilon transitions of accept states. Now what remains is only the transitions of the new state q0. So that's also very simple. So when what is delta q0a? This is actually the empty set when a is not epsilon, right? Because the only transition that is there is the epsilon transition, and when a is epsilon, it is nothing but the set q1. There is only one outgoing arrow, and that's it. This completes the construction, and hopefully the correctness is evident in this case, and as it was in the other three cases, other two cases, and that completes the proof that regular languages are closed under the star operation. So now you see, we saw that regular languages are closed under union, concatenation and star, and both or all the three proofs are fairly simple and fairly intuitive, and you could understand the proof and even the correctness by just looking at the figures of the pictures of the proofs, right? So of course we can formally define it, and I urge you to go through the formal proof which is there in the book, which we gave for the third case, but we didn't give for the first two cases, right? So using the power of NFAs, we are able to show that regular languages are closed under union, concatenation and star. We also saw closure under complement earlier, right? So that completes lecture 9. In next lecture, we will see yet another characterization of regular languages using expressions. Okay, thank you.